This is one of the talks where I'm happy that I have backup slides because most of the things I'm going to be talking about have already been said in many ways, shapes, or forms. So I'm really happy about that. That also shows that we have a collection of very good speakers today, right? So I'm going to be talking today about a very broad topic, sensing and actuation, specifically in the context of cities. This is work that I do with my colleagues at Carnegie Mellon University, where the Civil and Environmental Engineering Department has a program that specifically focuses on the application of information technologies to civil and environmental engineering problems, which is very appropriate for the context of this specific venue. And since we said that we wanted to take a very brief time, this is a lightning talk, I'm going to spell out right away what my key take-home messages are before I even dive into the talk. So I think I have two take-home messages. One of them has slightly been covered already. The first one is that I think the reason for why we want to use sensing and actuation in cities has to do with the very basic reason for why cities exist right now. And that is we have cities because cities are efficient at tapping into our resources. And this is the sublinear relationship that has been talked about before, Jeff West. And to take it to the next step, we're going to have to use some automation. It's not going to be enough to have us as humans dealing with all of this information and dealing with all the knobs and buttons that we have to press in order to make the city more efficient. So that's why we need sensing and instrumentation in general. The next point I wanted to make, and this is a second take-home message, is that to get to that point, we're going to need some sort of operating system for the city. We've talked about open data. That is one component of it. We're going to have to also rely on more fine-scale control and more fine-scale resource management for dealing with that. So, for example, the issues that have been raised about privacy, resource control, how do you get access to specific actuation mechanisms, and how do you control that it's not used for malevolent purposes. All those things need to be in place, and that's why you need an operating system. So those are my two take-home messages. I'm going to step back maybe a little bit far away, and I'm going to start with the Earth. So this is to give you a sense of why we actually need sensing and actuation. So we live in this planet. It's about 4.6 billion years old, and all of the energy resources we have at this moment come basically from two sources, either the Earth itself or the sun. On the Earth, we have nuclear energy and geothermal energy, and from the sun, all the others. The renewables that we know about are basically derived from the sun, and all the fossil fuels also derive from the sun. And the process of life itself is a process of trying to harness that in a more and more efficient way as life evolves, right? So we're trying to combat the second law of thermodynamics. We're trying to go away from being an entropy-driven system and trying to come up with better ways of harnessing that energy. So we went from single-celled organisms to multi-celled organisms because it was more efficient to harness energy. Then we went to full organisms that would allow you to harness the power of the sun and everything else. We went to communities of organisms because of that same reason, and now we are living in cities because of that same reason, right? So the key take-home message here is that cities are a great way of harnessing all those resources, but if we want to take them to the next step, and because there are problems of population growth and limited resources, we're going to have to include some kind of automation there. So the limited resources problem, I'll ask one question to put it into context. Right now we're consuming energy worldwide at about 2.6% increment each year. If we continue down this path, how long do you think it'll take for us to require all of the energy that the sun is producing? Is that 50 years? Is that 1 million years? Where is it? 500, I hear. No. 5,000. 50 years. Well, 50 is a very low number. The actual answer, if we continue at that rate, is 1,400 years, which if you think about it, modern history is older than that. Right? So we're going to have to be very careful about how we use those limited resources. We also have a very wasteful infrastructure that we need to better manage. So for example, these are basically fluorescent light bulbs placed right underneath a power line, and they're lit up by the electric field that's created by those power lines right away. Right, so we have a very inefficient power infrastructure and infrastructure in general. We have growing population, which has been talked about before, and we have aging infrastructure as well, which is one of the biggest problems. So we're going to have to move on from purely mechanical systems and systems that only recognize things that they're programmed to do, to systems that can act on their own, understand the environment, and deploy actions based on that understanding. And that's why we need both the sensing and the actuation at the other end. All of the data is pretty much there. We have a ton of sensors. We have humans acting as sensors in the real world. We have, as we have seen in the past few talks, an enormous amount of data available. Now the question is, how do you make it available for this next step? How do you make it accessible in an easy way, and how do you make it high quality? I think we need an operating system for that, specifically because we need an abstraction layer that allows you to access all of those resources in a common way. Open data is one way of getting that, but if you deal with the hardware that is out there and all of the protocols and all of the mess in the real world, we're going to have to do a little bit more work on that. Talking about actuation requires for us to talk about access control as well. Once you have access to changing things in the environment, you have to limit who is able to do so. And also ways of self-describing that data so that it's not only human interpretable, but also machine interpretable. We've been trying to put our little grain of sand into this problem, into this solution. We've built on Carnegie Mellon campus a project called Sensor Andrew, which is that middle point that allows sensors and physical systems to communicate and abstract all of that into the analytics world, the access from mobile phones and everything else. So if you're interested about that, that's another talk that could be given, but I know that many of you are also working in this field as well. I just wanted to point that out as one example of how do we build that operating system. Then 3 things to keep in mind. I think that it's been said before. I think Colin this morning said it. We need to be not only using technology for the purpose of using technology, but being smart about how we deploy it. So we already have infrastructure out there that is doing most of that sensing and most of that actuation. We may need to just be more intelligent about how we use it. I'll show 2 examples of that. We need to reuse that infrastructure, and we also need to be very sensitive about how we use control so that it's context-driven and not just controlling for the purpose of controlling. So in the last few slides, and this is why I'm glad that I brought backup slides, I'm going to show 3 projects that show basically those 3 points that I tried to make. So it's smarter edge nodes. We have meters in every home at this point in time, and it's not clear that if we want to get more information about how you're using your energy in your buildings, you need to actually deploy more infrastructure into the buildings. So my group has been working on trying to find out if from the meter itself you can identify fingerprints of when appliances are turning on and off. And so this smart metering infrastructure could be used by using one single sensor to measure individual appliances without having to deploy sensing in the home. We also have collaborated with the U.S. Army Corps of Engineers. They have a problem where they have tons of instrumentation on dams and levees, which are flood control infrastructure, and they don't know exactly how to predict when something is going wrong. So being more smart about how they use the information that they already have. And again, this is another example where humans are not sufficient. There's a ton of data that they have, and the big problem they have is that right now they don't have a way to actually analyze it in a speedy enough manner. Reuse of existing infrastructure, making, for example, use of existing thermostatically controlled loads in your home to store energy for balancing grid operations. That's one example of where we're trying to reuse information that's out there and infrastructure that is out there. So for example, using 1,000 refrigerators across the city to balance the power demands, or for example, when there's peak power, you try to shut off some refrigerators and then do that kind of balancing that the grid requires without having to deploy new infrastructure. And lastly, automated context-sensitive control. If we were to use, I'm going to use the same example, all of those refrigerators and all those loads, you will need to be careful about when you do that. And so it's not just about using it for the purpose of making sure that we have control and using it so far. I think it's more about knowing when to use it. So this picture just shows a funny little example of how batteries would be thinking about this problem. But the batteries themselves don't think about what the user is doing. So that's why I think knowing the context of when you're shutting off loads and when you're doing that control is important. So I'll have to go back just to give you the conclusion. I know I'm running right on time. We have a very bright future ahead of us for the new cities of the future. And to avoid going to the right-hand side into this very dark picture, it's not just enough to have brains in a jar. It's not just enough to have the analytics alone. We need to have that brain interact with the world through sensing and through actuation as well. So those two components are very important for the bright future that is ahead of us. Thank you.
Our next speaker is Jerry Walters of Fair and Piers on one of the most complex operational problems in the city, which is multimodal transportation. Jerry, you
would have thought I'd have learned from everybody else, but I'm
That should be, put it on.
okay.
Yeah. Okay.
We're up. Thank you. Okay, you can deduct that from my time. You already have. My name is Jerry Walters. I'm with Fair and Piers. We're transportation consultants with offices throughout the Western U.S. and projects scattered throughout the world. And I'm going to start from the outside in on urban transportation. I'm going to talk a little bit about the big picture issues and how the dynamics work in multimodal transportation in urban settings. And I have about 9.5 minutes left this morning, and then I get a second bite at the apple this afternoon. I'm going to dive in a bit deeper this afternoon. But in both discussions, I'm going to be generally operating within this virtual set of cycles. The first is the planning and getting ready and approving transportation and land use development in an integrated pattern. Those processes are fundamental to then what we need to operate after the fact and how we use what we learn from what we're operating to make more conscientious, well-advised decisions in the first place. So the process in our way of doing the analysis, the heart of it lies in simulating what the outcomes are likely to be of a prospective policy or plan that informs both the planning, the evaluation, and the decision-making on what to either approve or to reiterate, which then takes us, when we finally get it right in the planning stage, to the design and operation stage of what we're doing. That cycle folds back on the planning cycle so that we can learn from it. So the monitoring and management of the operating system that informs us through analysis and through simulation of how to continue to improve and refine and make better decisions. Jeff West tells us, and everybody seems to be familiar with his work, that scale matters, that as we go to larger scale mammals or urban environments, we become more efficient in terms of BTUs or energy per pound of mammal or per capita of city. Also, we get the productivity advantage. As we become larger, at least in the city form, productivity and creativity increases in urban environments. But the critical question is, do we have the skeletal system and the circulatory system, et cetera, to operate those systems in the city, or do they collapse on themselves? And that is our job. The way we understand how scales matter is at the more nuanced level of going into the individual ingredients. And we've been able in transportation and land use interactions to define that in terms of at least 8 critical dimensions. Density, of course, diversity, the mix of land uses, the jobs housing balances, the services balance in total, and also how well integrated they are within the urban environment. Urban design, the network density, the interconnectivity of the transportation networks is important. Destination accessibility, critical, and we can measure these, and I'll talk a little bit about those. The others are relatively self-evident. What we've been able to do, and this comes from one particular study, which is a study of 260 or so mixed-use development projects around the US, totaling about 800,000 trips, is develop probabilistic formulae for predicting vehicle trip and travel generation as a function of those 8 dimensions on the previous slides. We've been able to resolve this into a dashboard for decision-making, so a development proposal can be evaluated as to its travel generation, its GHG emissions, its opportunity for shared parking, any number of transportation outcomes. And we can use that to inform decisions. So I'm going to go quickly through a few case studies this morning, and then, as I said, drill deeper this afternoon. First one is a planning environment, an operating environment that is an engine on the run. Planning in China happens on the fly, and the design decisions are made often before the planning decisions are made. This particular study is one relating to a new town in southwestern China called Kunming. And the question of whether business as usual in terms of urban design in China should continue as usual with the relatively macro scale, not only of density, but with regard to the transportation network. You can see if you look closely, the street system seems, number one, it seems to be operating fairly well, especially in the lower photograph where travel hasn't begun yet. The project's still under development. But one critical aspect of that, and there's more to the story on the next slide, is the distance to cross the street for a pedestrian in either of these environments is about half a football field. So the accommodation for other modes of transportation is an afterthought. The operation of the transportation network is, in fact, an unintended consequence. Because what really happens when they open for traffic is it begins to look something like this. So it's not a hospitable urban environment either for traffic movement or for pedestrians, bicycles, rickshaws, et cetera. So what we have been able to do in this Kunming example is about 500,000 people in terms of jobs and employment. And the objectives in this planning exercise were to make it more sustainable. Altruistically, those are the objectives. The challenges in China are the pace of development, as I said, often doesn't allow careful, deliberate planning. The planning process is already governed by mandates that are established based on 1950s design principles in the US. Car culture is growing, and there are just data and models for at least transportation planning are either heavily guarded or non-existent in China. And at the micro level, the planning just doesn't work well when you hit the street. So at the very simple planning level, we look at it in this fashion. Sesame Street asks us which of these is not like the others. It's Beijing in the lower right-hand corner, compared with New York, Portland, and San Francisco. The urban design context just isn't complete. The comparative concepts then compared for evaluation in Kunming were one that took the conventional plan, in fact, in place, and refined that through a finer grained network, use of couplets for transit and traffic, and sightlines and guidelines that created urban character. And the evaluation of that then through simulation of the traffic and transportation operations told us that when we moved from the macro urban design to the micro design, we moved from report cards on the top bar there. The E's and F's are what they mean on any report card, failing traffic conditions. The A's, B's, and C's in the lower diagram are the operation of the more refined network. And this does not even take into account the fact that because of those D's that I talked about earlier, the density, the diversity, the mix of use, actually would reduce travel generation by about 9%. We didn't take that into account in this analysis, nor the dispersion of traffic over the network. This is same traffic volumes in two networks. And the bottom line parameters, because pedestrians cross the street more efficiently, because the traffic signals are simpler to operate, we reduce the poor levels of service, we reduce by 25 to 18% travel times, energy consumption, and emissions. Now a California example, very different operating environment. Here, sustainability is essentially job one, given the laws we've recently passed. Streamlining sustainable development, incentivizing it through grant programs and the like. That operating environment also includes our DOT. Caltrans has operated into the smart mobility framework now with new performance standards that talk about location efficiency, network management, and multimodal focus. And our air pollution control officers in California have set up a hierarchy of demand management strategies and a network of how they interact with one another that we can plan around. So the working example of that is planning policies as they relate to our main new infrastructure possibility in California, high-speed rail, developing a dynamic process to evaluate the land use policies, the transportation infrastructure, and the outcomes in terms of the triple bottom line of environmental, economic, and social consequence. Inside the computer, we have a grid cell network of about 9 million 5-acre grid cells masking the entire state that's populated, operating through those analytics that I talked about a little while ago, calibrated against real travel environments. So on your left, we see the model estimate versus reality in terms of vehicle mile generation in different sub-communities within a greater region. And we see a good match there. What the engine then allows us to do, this GIS-based transportation analytics, allows us to evaluate land use, policy, strategy, and infrastructure in ways that, along these metrics and a batch of others, produce between a 25 and 33% improvement in VMT, GHG, energy consumption. So I'll be back this afternoon to talk a little bit more about the right side of the loop, how the operations and how we measure that feeds back into the simulation that I've just been talking about and allows us to make those transportation decisions. Thank you.
Jerry, thank you very much. I think you're one of the first speakers, I think, to touch on a fascinating and difficult problem in this space, which is the interactions between these multiple systems. And we'll come back to that topic, I'm sure, again. Our next speaker is a colleague from IBM, Jayant Kalagnam, from our Math Sciences group, talking about resource management in cities.
Thanks, Colin. Good morning. I'll take the 10 minutes to talk about resource management, especially with a focus on efficiency and efficient provisioning, which I think is an important imperative for growth, sustainable growth. We heard earlier today discussions about urbanization and how the population of cities is growing. And as we can imagine, as a result of this massive growth in demand, the need and the demand on urban services and resources would grow dramatically. If you think about urban infrastructure like transport or energy and electricity and water, with populations going up to maybe even twice today's level, especially in Asia, the demand for infrastructure would also be very high. Clearly, most cities are not in a position to double the total infrastructure in cities. So the question is, how can one, as a city official, think about provisioning for this greater demand? So the main point of my talk in the 10 minutes I hope to make is the approaches that we need to think about, which is another dimension of all the discussions we're having today, is how do we use the information coupled with intelligence to better and more efficiently provision for demand from within existing infrastructure resources. And I think there are really three threads to this thought, right? One is demand management. A lot of what we do today in terms of how we provision for demand tends to be over-provisioned. And part of it is because we provision for peak demand, and most of the other times of the day or other places in space, we probably don't need the same peak demand. Another reason is for availability. We want reliable systems, and hence we over-provision because of that. And finally, I think this is a point that got alluded to many times today. We often provision and plan for aggregate descriptions of demand. And now we are in a position where we can get a very fine-grained understanding, both spatially and temporally, of micro demand. And if we are able to provision, keeping that in mind, we could get much higher efficiencies. So those are the sort of main points that I want to make today. So I'll just quickly get through some examples to talk about this, right? So demand shaping, a very typical example for electricity. This is what the load for electricity looks like for a typical day in sort of the northeastern climates. And one of the big questions about doing better with existing infrastructure is, can I shift demand from peak to off-peak periods? Right? A classic question in economics, we talk about this as demand management. But in order to operationalize this notion of how to do demand management, we need to think about multiple systems, right? First, at the level of buildings themselves, of different kinds, right? Buildings, either residential or commercial, and understand and model these buildings both in terms of what is their energy demand, depending on various external factors like weather, and also understanding the behavior and occupancy of the buildings, right? Which in turn then allows us to think about how the need for energy would respond to signals that we provide externally, either in terms of price incentives or other rebates. If we had such a picture of buildings, what might that do in terms of thinking about cities? This particular slide shows a picture of a distribution feeder network for a city. Typically, for each street, which is shown along the rows, you might have different demand classes in terms of either residential or commercial. And the kind of model that I showed earlier in terms of understanding demand at the building level could then be mapped into this feeder network, which would then allow us at any aggregate point in the feeder network to understand how this demand could be responsive at an aggregate level, right? And therefore, the idea of being able to dispatch or move demand over time or maybe over space. There are many such experiments underway in the country today, right? This is an example from what is being done right now in the Pacific Northwest as a DOE project, where the idea essentially is to overlay an information network on top of the power grid, where each node of the grid provides a framework that allows us to model assets at various levels, both residential and renewable energy kind of assets, so that these assets are responsive as the information flows both from a demand perspective up into the grid, and also in terms of incentive structures or incentive signals that go down to either the buildings or to other renewable assets. Okay, so that was this question of what do I do with demand and how do I shift demand. I want to take another example also from the electricity and energy space to talk about how we do with availability, right? So typical scheduling of generation planning for demand, which often tends, which is shown here, which often is quite uncertain, is done in a way to provision with some spinning reserve so that if there is fluctuation that has not been planned for, we still have high levels of reliability. Add to this renewable energy, which often is being regulated as being required, you have higher intermittency for which you need to provide higher spinning reserves. And of course, the question is if we added more spinning reserves, it might actually have a higher impact on the carbon footprint. And the question is, can we actually improve the way we do analytics to allow us to model the stochastics that happen with this in a way where with the same infrastructure, we can still get the high level of availability. And what I've shown here is an example, which is just for indicative purposes, where if we were to model the stochastics explicitly, which is shown on the left-hand side, as compared to what we do today, which is just to put a 15% spinning reserve to manage for the intermittency, we can still actually, with the same infrastructure, achieve the same reliability at lower cost or at a lower carbon footprint. And the last example I wanted to talk about, I'm going to skip through slides in the interest of time, is transportation services. This is another example where a lot of cities are thinking about how to provision for a much bigger population as the number of people in cities grow. Right? I was in Singapore for a few months recently, and it turns out that in Singapore at peak times, the demand is growing quite a bit, and the city is now faced with a question of should they put in more capacity, right? But here's another very interesting example where, indeed, increasingly, because of mobile devices that most people have, and somebody mentioned earlier today, Singapore, everybody seems to have 2 smart devices in hand. These devices might allow us to get a very clear and a very high-resolution picture in terms of trip demand, both in spatial and temporal dimensions, right? Which would allow us to actually plan for provisioning for these sorts of trip demands in such a way that we can use a fleet of vehicles to design trips which still provide very high service levels, at the same time provide very high occupancy. So with using a fleet of cars or taxis for a city like, say, Singapore, we might still be able to provision for a much larger population, but by getting higher occupancies, right? And a simple example in terms of how this would work is if mobile apps were used to elicit from people their trip demands, one could rethink the way we do provisioning in terms of designing trips on the fly in terms of resource management. And I've shown this here with different colors to sort of send different vehicles for different people so that trips are designed to pick them up and drop them off. And in fact, a pilot such as this is being tried out in Tokyo, right? Which would allow us to actually use movement and mobility data from handheld devices to build transit systems by understanding both data from a GPS perspective and also from the CDR data, which is the call data records, to understand a very micro-scale picture of demand and hence do very efficient provisioning. So in conclusion, my sort of main point I wanted to emphasize is the ability to provision for very fine-grained understanding of demand would lead to much higher efficiency in the way we use infrastructure. Thanks.
Great. Thank you very, very much, Giant, especially for standing in at very short notice for Constantine, who couldn't be with us. So Yuri is going to now do his impersonation of Peter Williams, who is Chief Technology Officer for Water Management at IBM. Peter actually lives in the Bay Area but couldn't be with us this morning. He will be with us this afternoon.
You know, when I got this presentation to pitch, I looked at the title and I thought, bloody hell, how am I going to do this in 10 minutes? But Pete's actually done an incredible job at summarizing the key issues and then in one flourish at the end explaining how it's all going to get fixed. So don't blame me for his conclusions. So it looks like in the Bay Area we've got a bit of a problem. It seems like people are being more conservative about the water usage in the sense, a true sense of conservation. Since the population's growing somewhat, as you can see, and the actual usage of water is really not. This is the overall use and this is the residential use. As you probably know, industrial use is dominated by things like factories and agricultural. And if you look at where the water's coming from and what's happening to it, you'll see an interesting story. It turns out, however, that droughts don't help things very much. And so if you look at the supplies of water, and you'll forgive my pronunciation of these rivers, Makalomni, how do you say that? The what? Makwalmi, okay, and that must be Tuolmini, by abstraction. So there's a state water project and the Central Valley project that take the water from the delta. There's local groundwater and there's a small amount of water of desalination. One of the things that we find all around the world is, and some claim it's because of global warming, but some claim because it's the density of people in cities. But for example, in Singapore, where they recycle a lot of water, one of their challenges is dealing with the groundwater and the water that comes from the sky, since it happens to come in such huge jumps in large volume increases. They're not used to the kind of volumes that they're getting, and it seems this is not unusual all around the world. So these sources are subject to a number of issues. So if you look at with the water from the Sierra Nevada, there's a number of problems there. The supply reductions are happening. As I mentioned before, as more precipitation comes, it's more difficult to capture it with the existing infrastructure. In addition, there's things like the Hetch Hetchy and Don Pedro reservoirs are under some stress. Apparently, the Hetch Hetchy's problem is that they want to take it apart. And it turns out it's not true? Oh, it is true, but you see, okay. There's a vote for no here, I think. It turns out, though, that the water in the Hetch Hetchy reservoir is actually some of the purest sources of water available in this whole region. And, you know, I don't know, I'm not going to make any social comment because I'm going to put my foot in it, I can see. If you look at the challenges in the Delta water region, the droughts are really making this worse and worse. And as you can see, already between about 30% of the water comes from these areas. And as more sea ingresses into the Delta region, it's going to get harder and harder to deal with that water. In addition, if you look at the pollution that covers the Delta region, especially in low flow periods, there's a fair amount of various halogens, as you can see, and also organic carbon. Nitrate's pretty bad. If you see nitrate in water, you know there's a bit of a problem with sewage somewhere or other. And then if you look at the groundwater, it's becoming overdrawn. There's various additives, and many of the gas stations that we put in place have the anti-knock agent put in them, and that anti-knock agent leaks into the ground and has a number of deleterious effects to life, as I understand it. And then the saltwater incursion. And as you can see, many of the rivers, much of the region is polluted from many industrial and various other sources. So, although the area is growing in population and people are being more protective and conservative in the use of the water, this is still going to hit us. If you look then at the economic impact, the numbers up here sort of speak to themselves. The infrastructure, like myself, is getting aging and it's seismically vulnerable. I'm not seismically vulnerable, but you get the point. And the storm drainage systems are really a bit of a problem. In some areas, the combined water sewer systems that were put in 50 years ago lead to significant problems. I saw this one unbelievable YouTube video. I think it was in Pennsylvania, where there was a 10-foot diameter manhole cover that was covering some part of the interstate, some large road, just blown up several tens of feet in the air, thanks to the sewage that was coming in, that was being blown in from the excess water that's coming in through the drains. Quite dramatic, and as you can imagine, in older areas that are 30, 40, 50 years that were built with these systems, it's a problem. So the other thing is there's a number of water rights and legal access to the water. I know Pete was working in Sonoma with a number of groups there, a number of agencies, and in order for some of the towns to be able to make sure they have enough water, they were pumping up so much water from the region that the remaining towns had no access to any water, that their pumps were actually cavitating because there was hardly any water in the ground to pump out. And it's because people had no joint view of what was there. They had no joint view of how it was affecting each other, that they acted as anybody rationally would act. They sort of dealt with their own problems since there was no information. And so some of the possible responses, wherever we see IT, it's really data that's made available. So obviously, continued conservation. You can't conserve that which you don't measure. Therefore, metering and monitoring is very important. We did a project in Washington, D.C. some time ago, and it was kind of interesting. Washington, D.C. has a network of several thousand miles of water and sewer, and one of the things is that the infrastructure dates back to pre-Civil War days. So they had a fair amount of data. They'd done a very good job in managing and storing the information, but there was so much data it was impossible to figure out what to do with it. We started looking at analysis of the data, and interestingly enough, in some areas, we saw that through the main lines there was a lot of water going into certain areas, but miraculously there was no water being paid for in those very areas. Turns out some handy plumbers had come into laundromats and bypassed the water meter, this kind of thing. So putting meters in might not be enough. You need to have meters to check the meters. Actually, mathematics can do that very well, right? So if you look at Mario Burgess' work, what he didn't show you was earlier on they built this set of metering systems to manage and meter electrical power in a home. And you could tell by the current excursions over time, sort of millisecond timescales, that a refrigerator had just turned on, right? You could tell that for a certain period of time, there was a peak power that went off in about 2 or 3 minutes. So you could infer, right, Mario, that what was actually going on, you didn't have to have a meter on every bloody device. And so you can do the same thing with water. If you look at the patterns, from the patterns you can discern what's actually going on, and from that you can start making decisions. You've seen this chart for long enough, but this continuous analytics-based detection and pressure management can really help a lot. If you look at what happens in many cities today, the water pressure is left on overnight. And in many cities, there's about 20% leakage of water. And by just reducing the pressure by a small amount, you can reduce that leakage significantly. Just simple things like that. Building hydraulic models that help you decide where to put valves. Some of these valves can be extremely expensive. and sort of managing the overall infrastructure with good data, good analytics can do quite a lot. Obviously, there's not much you can do in terms of dealing with seismic fragility except improve your infrastructure. I mean, it's going to be seismic, but you need to be able to understand the risk. What we found in more cases than anywhere else is, yeah, you can predict which pipes are going to break. You can predict which infrastructure is going to be bad. But what the people who own this infrastructure really want to know is, how much money am I going to need next year for my budget to fix this stuff? So predicting is good, but the first stage of prediction, because nobody's going to dig up a road if you tell them that pipe's going to leak. And so what we'll do is, as long as you can, the first case, predict how much money you're going to need, it's a good start. And there, ladies and gentlemen, end of the lesson in exactly 10 minutes.
Thank you very much, Yuri. Great imitation. I should commend you to Peter this afternoon. And now to Keith Besserud of Skidmore, Owings and Merrill.
Okay. All right. So I think I have sort of the final lightning talk here before Colin will get us sort of back up to speed on where we're going. And I'm going to close here with a sort of a summation of the exercise that sort of preceded this one in a way. We had a workshop session in Chicago that was sort of a mini event, as we characterized it, that maybe led to some of the ideas that are going to play out here in the rest of the afternoon and into tomorrow. And also, I realize, as has been realized before, when you're sort of the last in line, a lot of what you have to say might get is sort of a reiteration of what's happened earlier, and I'm sort of starting out that way. And this is sort of the idea that led to the workshop in Chicago is the idea that looking at cities as these infrastructural and spatial contexts where people come together to engage with each other in transactions for a wide variety of reasons. And sort of repeating some of the things that have been said earlier today. And that the underlying currency that allows for these transactions to happen is information. So a question then is, can a better understanding of these flows of information allow us to create and operate better cities? And I think we all believe the answer to that is yes. And so in the Chicago experiment, then the idea is what can we make start to develop a map of these information flows, or this idea of a information flow map. And so that was sort of the premise for the exercise, for the experiment. And it really was an experiment. I think we sort of bumped our heads in a number of cases that sort of, as I said, paved the way for this meeting. So the way we framed it was as to take a look at a case scenario for something that happens frequently in an urban context, which is the development of a real estate project. So we had a case study in Chicago that we sort of used as a focal point, which was this Lakeshore East development in the downtown area of the city. And the exercise was basically to try to bring together some of the players that were involved in the project to talk about how information flowed from one entity to another in the course of realizing the project. So we had the developer, which was an organization called Magellan. SOM happened to be the urban designer on the project. There were obviously many city agencies involved in the project, but we looked specifically at a group called the Department of Housing and Economic Development. And then there was a local community component involved in the experiment as well, a group called the Grant Park Conservancy. And so the idea was to try to bring these people together and have a conversation about information flows and how those information flows were vital to the way that the project progressed. Before we got together, we tried to sort of prime the participants with a series of questions and met with them beforehand even. The objective was to have them come to the meeting with some idea of these information flows from their particular domain already sort of mapped out in order to be able to engage in a discussion about how we sort of moved across domains. And these are some of the questions that we asked them to think about as they were preparing their diagrams and their slides to facilitate the conversations. So the flow diagrams that sort of emerged then that they came with were of a variety, clearly. And I'll start with the one that came, and I was not the representative of SOM in this case. We had one of our senior designers in the urban design group that played that role. And this was the chart, these are the charts that he developed to try to explain from an urban design perspective how we were dealing with the dynamics and the information that were involved in doing a project like this. So in this chart, explaining our relationship to the client, to the public, and then to all of the various consultants that are involved, just to give a snapshot of sort of the wide range of people we engage with, and as you can sort of imagine, the types of information that are coming from each one of these players. Within the overall urban development process, we're focused on just one piece of that, which is the master planning process. So you can see all these other steps along the timeline that are outside of that domain. So again, trying to sort of focus for the purpose of the exercise. And within that master plan process, then there are several steps or components that we move through. These are sort of suggesting a linear process, but I think we all recognize that it's not a purely linear process. There's a lot of feedback looping that happens within these processes. But within this sort of quasi-linear process, looking at each point in the process, so there's a sequential element to all of this as well, of needing different types of information and producing different types of information at various junctures along the whole process. So starting at a phase of analysis where we're trying to take in information about the project, about the site, about the different players, about the issues that are driving things, moving into the planning process and bringing to bear, from our perspective, a philosophical point about design and what is important, what we perceive to be important, and bringing that information into the process, which then leads to the conceptualization of the physical aspects of the project. And as you can, again, imagine from all of these different topics, the amount of information, the types of information that are trying to feed into the process. Ultimately, this yields a master plan, which is documented and provides a rich amount of information to move forward. Then that ultimately, hopefully, become policies in terms of design guidelines and that sort of thing that have staying power as the project moves forward into the later stages on that bigger timeline that I showed at the beginning. This is the slide, and I know you can't read this. I can barely read it myself, but that came from the city agency, and what was interesting in this one, they were able to sort of key into this idea of information flows in a certain way, but this idea of efficiency, I think, is sort of reflected in the way that they're identifying the different topics and pieces of information and information flows, and sort of keyed me into this idea of how the city looks at this in a very unique way. And then the community group, I think, had a harder time sort of getting their heads around this whole idea in a way, but made a very important point here. I think that they are sort of on the receiving end of information. They have a harder time to move into a driving position in the process, and so what this slide is showing is how, depending on the project, they enter the process at different points depending on when they get pulled in or are able to sort of, wrestle their way into the process. And then finally was the developer who just couldn't seem to really get his head around it at all in terms of trying to think about what he does as a discrete process or management of discrete pieces of information. However, in the course of the meeting, we had a lot of great discussion. I think as the discussion warmed up, he was able to plug into it much more effectively than sort of coming at it cold. So some of the takeaways, we talked about the importance of the social aspect of all of this stuff, and I think it became very apparent in the process of trying to run this exercise in Chicago was that people are not accustomed to describing what they do, in terms of steps of a process. And I think that they're even less accustomed to thinking about the information they work with as tangible, discrete things. And so it takes a while to sort of get them in thinking about these problems in these ways that we were trying to address. In general, everybody wants as much information as possible as early in the process as possible. That's sort of a truism. But the developer pointed out, obviously from his perspective, there's good reasons why he has to withhold information, certainly at the beginning, because he can't put stuff out there that he doesn't even understand the feasibility of it yet, for example. Or there's political protocols where the alderman of the district where he's going to be working in feels like they need to be the first one to know about anything. So there's those kinds of components that need to be understood in terms of an information flow map as well. And interestingly, there were very few, there was very little ability for these people to talk about yardsticks of success. So we had this development that we were sort of focusing on the Lakeshore East project, and if you ask the city agency, they said it's a very successful project. Everybody considered it a successful project, but how do you measure that success? They were without an answer. Well, it looks great. It has beautiful buildings. It has a beautiful park. So there's that dimension. But in terms of actual sort of quantifiable, economic or social or whatever kind of data, there's nothing that is built into the system to track that. And even for the developer, which I'm sure there was return on investment data that was critical to understanding the success of it. But beyond that, he was kind of like, well, we've got great retention rates on the renters. So, that tells us that it's a successful project. So it was interesting that, again, in terms of thinking about the terminology that we're using and the concepts that we're talking about, just even the idea of success was a little elusive. Interestingly, the discussion at the point in the day when we were talking about the participation of the community groups, I think this was the part that really sort of lit the discussion the most. I think people were really, really interested in this. And it highlighted a number of questions, like what are the limits of the community's right to information about a private development? How does the community group leadership itself gain credibility? It was interesting that at one point the community group leader talked in terms of having to be sort of an educator of his constituency about what is good design and telling them, you don't want this, you want that. And it was almost like another layer working its way in between the community and the process. I thought that was kind of interesting. And then just the question of how can a community engage effectively in a design process. And obviously we've seen some discussion about that already this morning, but I think there's all kinds of room for innovation with respect to again, this very narrow segment, the development of a real estate project, in terms of finding better ways to engage the community. And then at lunchtime, we had a great presentation from Bob Schloss at IBM about some modeling work that his team is working on that's looking, from the presentation, it appears anyway, that at a very, very deep level of this idea of information transactions and capturing that in a model. And then obviously there's still work to be done in terms of trying to find a convention, a graphical convention, I think, for communicating these ideas. I think it falls somewhere maybe in between these two realms. One of the organizers of the event was coming from this sort of Gantt chart perspective of a timeline idea. I was thinking initially more in terms of some sort of a network diagram. Neither one of them fully captures the idea, I don't think, that we're trying to capture here. So I think there's some interesting work to do to begin to understand that. And one of the places it occurs to me to maybe look is the world of biology, which I think it appears that, I mean, the science of biology is very much about flows of information now, and this is an image from the Human Connectome project, and I'm thinking there might be some things that we could pick up there. Is there an idea called an urban connectome? That is what we're actually sort of pursuing here, so. Okay, and that's it.
All right. Well, first of all, my thanks to the speakers. We are miraculously almost exactly on time. Last year, when we ran the first of these meetings in New York City at NYU, we had a smaller number of speakers, and I think we had allocated 20 minutes for each of the speakers on panels. One of the speakers was Jeff West, and how many of you ever seen Jeff talk? You've probably seen some of his videos. He's a fantastic talker, and of course the scaling law business is a great story to talk about. However, we couldn't stop him at 20 minutes. I tried to stop the talk after an hour, and the audience argued with me. And I think he actually went on for, about an hour and 40 minutes, something like that. I mean, we were all just enjoying it, but it did kind of ruin the schedule. So anyway, so thanks for that. But thanks also for showing some of the multiplicity of views that emerge in this space. This is one of the reasons I have found for several years this area so absolutely fascinating, that as we begin to look at the complex systems of urban systems, urban infrastructure, urban living, through this lens of information, we realize what a rich new set of perspectives it gives us on what is going on. As you saw Jen talk, this point I picked up on there, which is, what is it that people are trying to do? People come to San Francisco, they come to Berkeley to live their lives, and some of that activity is essentially hidden, but some of it depends on how much the city, the urban environment, facilitates the kind of life that people are trying to lead. How much does what the city provides actually correspond to what people are trying to do? I think one of the fascinating experiments that Yuri's team at IBM Research has done the last couple of years, initially in a little living lab that where we've developed a collaboration over the last several years, the city of Dubuque in Iowa, and then later on in a much bigger context in Istanbul, has been to look at how do public transit routes, many of which have not been changed for decades, correspond to the journeys that people actually want to take. Dubuque is an interesting city in many ways. It's an old mill town, used to mill wood, and its industrial district died 20 or 30 years ago. But when you look at the journeys that people are trying to make through that city, the bus routes still correspond to the time when the city had a thriving industrial district. And the researchers were able to show that, in fact, there was the transit system had essentially a 30% overcapacity because it was so inefficiently constructed. So now we're looking at applying that in Istanbul. So it gives us this ability to look abstractly at what is going on in the city, what capabilities does it provide, what capabilities are the citizens making use of. Because it's abstract, we can aggregate it, we can look forward in time, we can look backwards in time, we can look across boundaries so that we can look at interactions between transportation and energy, or water and energy, or climate, or weather, and many other dimensions. So it gives us, among other things, the ability not just to guess what is about to happen, what may happen tomorrow, but to actually have very good predictions for doing it. And as certainly in IBM, I've looked at many cities in the last several years. In many cases, that data already exists. One of the fun pieces of work that the Math Sciences group did 3 or 4 years ago came from Singapore, from the Land Transportation Agency there, which had built a road pricing system in the 1990s with many gantries to detect the passage of a vehicle. These are transactional systems. They have very good business models of their own, but they have this sort of data exhaust side effect of collecting very detailed information about the movement of data. And the Land Transportation Agency had come to us and said, you know, we have all this data piling up here. Is there anything useful we could do with it? And in fact, what the mathematicians were able to show was, well, you can actually use it to predict congestion with very, very high reliability. So this is a whole new perspective. Steve Koonin, I thought, had this brilliant idea of, you know, turning telescopes around to look back at the Earth. And in fact, in many ways, those telescopes already exist. We can see already enormous amounts of detail about what's going on in a city. And our challenge now is to figure out how do we use that to make better cities. Of course, it depends on what we think better makes. So anyway, a great start, a wonderful morning, and again, I thank the speakers very much. It is now time exactly for lunch. We will reconvene at 1:30. We'll spend the afternoon in 3 panels looking at 3 of the major areas that we've touched on. Actually, one that we haven't touched on very much is the impact of this approach on governance. How does this change the way we think about interactions between cities and the city government? So 3 panels. We'll finish, I think we finish about 6 o'clock, is it? Right. And after that is the reception over at Worcester Hall, which is less than a 5-minute walk from here. So I wish you all a good lunch and look forward to a great afternoon too. Thank you.